K5 coefficient of static friction sushi on vinyl. I was inspired to make this problem from a photograph I saw in Flickr, Sennuchi Kuroki. And here, put sushi on the old turntable. I used to have one of these. And here, some of these have variable speeds where you can speed up a little bit. So we're assuming that we have a variable speed here that we could reach 80 RPMs. With 80 RPMs, we find that an 8-gram piece of sushi, 3 centimeters from the center, starts to slide. What is the coefficient of static friction? Because you reach the maximum, it's starting to slip off. So to do this problem, part 1, we want to find out US, given that at 80 RPM, 8 grams for the mass and a distance of 3 centimeters, slipping starts to occur. And then 2, relate this problem to one that we did earlier, where you take the vinyl record and the sushi, and you basically, what you do is you make the angle like we did earlier, where we had a slant, and then put the mass on there and keep increasing this angle and see when that starts to slide. So we're gonna look at that and see what angle it is. And we want things in terms of the basic parameters, which says basic parameters are going to be omega. It says angular velocity is your basic parameter. Your mass is a basic parameter. Of course, gravity, g, like this. And the distance you are from the center. So these are basic properties. Now, if we set this problem up, we have here a top view, and we have here some R to get to the sushi of mass M, and there's a static friction, and we're going around like this. So what is going on with the sushi? Well, if you put the sushi here, you have mg going straight down. So now we're looking at a side view. This is a side view. This view here is top view. So now you look on the edge, the side, with the sushi sitting on the record. You have mg going down, you have a normal force going up, and you have here the force that's keeping it going in a circle is your centripetal force. And then when you reach the maximum, it starts to slide. The static friction, you exceed it, and you start to slide. So let's look at this. The friction is always going to be mu n when you're at the maximum effect, and this is mu smg. So if you wanted to write this out the way we usually do, F is m v squared over r, and then n minus mg equals to 0. So like the net force here in the horizontal direction, go ahead and call that positive. And that direction is mv squared over r toward the center. And then n, if I call that positive, going up, then n minus mg is 0. And then I have my auxiliary equation, friction. So these two get me here. N is mg, and F is mu sn. So this gets me mu smg, which after practice you start to write down, without doing all these steps. And then this is your friction is your force that's holding the sushi in. So when we do that, here we go. Goes in there, comes down here, mu s mg equals m v squared over r. And we see immediately the mass goes out. So it doesn't matter what the mass of the sushi is. It's going to work regardless. So therefore, mu sub s is going to be v squared over gr. We've seen problems before where gr and v squared shows up a lot. Ratio is dimensionless. But we're not finished because we need to have v expressed as omega r. This is your connection between the angular velocity and the tangential velocity, see, which is this way, v. And remember, you have velocity, you have in a circle, you have v squared over r. So we need to get rid of that, and that's going to be omega squared r squared over gr. One of the r's drop out, and we get this, and this is the equation we want. We want the omega squared r over g. This is the real answer to the problem. So we'll put 2 boxes to emphasize that. Then for part 2, we go to, it also asked, by the way, for what the values are. So this problem wanted to have a nice formula, and then it wanted to have the numerical answer. That was also in the question. So we wanted to have a theory and nice practical engineering problem to work out the numbers. So if we want the numbers here, omega is 80 RPMs. Each rotation is 2 pi, and that's per 60 seconds. So this is the rads per second, 80 RPM. So it's 80 times 2 pi per minute, per 60 seconds. So when we do that, zeros cancel. 2 goes into the 6 3 times. You get 8/3 pi rads per second. Then we need to square that. So we have 8/3 pi rads per second. I'll just put per second. The rads, the rads are implied. And then I have r over g, which is 3 centimeters, 0.03 meters, over 9.8 meters per second squared. And that comes out to be, when you work all that out, you get for mu s, if you work this numerical part out, we're gonna get mu s is 0.21485, and then we want to get significant figures right. There we go. So this is the answer to part 1. It wants to know what the angle is in the case where you have a slant like this and the thing just starts to slide down. Now, we did this problem before here with the book and depending on the book, and we have to reproduce it here. So it's a good review to reproduce this. So if we reproduce this with an axis that's tilted, we have mg going down for the sushi, and this angle here, if I slant this slant here is this slant. So that means if I go dot 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 there, this is the angle theta. It's complementary to this angle, since that's a right angle here, right triangle. So this has to be then theta over there again. Then I have a normal force. See, I have the gravity, I have the normal force, and then I have the static friction. that's going to be at its maximum right when it starts to slide. So if I sum the forces down the incline, I have, see, I'm going to make this as the positive. So I have mg sine of theta, mg sine of theta, opposite side is going to be this one, say, and that's going to be then minus Fs is mass times acceleration, which is 0. It just budges, all right? And then for the other direction, we'll call this positive, I have n minus, this is mg cosine of theta, gets you the one going along this direction, and that's equal to 0. And I have the auxiliary equation. So these two will get me n is mg cosine theta, and then Fs multiplied by the coefficient of static friction. We get this. It's a good review. Then what we do is we plug this in this equation. Well, see, this top equation here is just simply saying mg sine of theta equals Fs, since the acceleration is 0. So this goes in here. Masses cancel once again. I'll just write this out. Mg sine theta is mu s mg cosine theta. So the masses go. And here also the g's go. So you get sine of theta is mu s cosine of theta. And that gets us mu s is the tangent of theta. And if you then find, measure that angle, you can then get that result. Now, the question here was find the angle. That's the question. So the angle is the arctangent of mu s, but we have mu s already in terms of the basic properties in the problem, the fundamental properties in the problem. So that means the theta is the arctangent of omega squared r over g. So this is the nice formula for the second part of the problem. And now we're ready to plug in the numbers to see what the angle is going to be. But we already did figure out what this whole thing in here is. We already figured that out to be all this part in here before we round it off is 0.21485. So really we just take the arctangent of that and then we're finished. So theta is the arctangent of this thing here. So with the calculator, that gets us theta is 12 degrees. A very nice problem that relates to something we did earlier in the course. And I like these general formulas, and I also like the numbers. So it's like we have theoretical physics and engineering have the best of both worlds in a problem like this.